Good afternoon and welcome to my laboratory. What you're looking at there is one of my Joule Thief test beds. This one I have set up so that I can change transistors easily, and then I also have 3 different coil arrangements that I can plug into the coil block there. These are just some extra transistors there, just stored there. So I have the on-off switch and the connector where the transistor is mounted, emitter base collector. That's a 2n2222a transistor. That's a blue LED. That's a 600 ohm resistor in the base leg. That's the block to connect the coils. And all of these coils are 1-to-1 windings. They have the same number of turns. This is a toroid that I wound myself with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think it's got 18 turns total on it. These two are little D-frame inductors that I pulled out of old television sets. And they work pretty well. As far as I can tell, both windings on these have the same number of turns. I don't know how many turns there are. Probably 50 or 100, but they're both the same. And so right now I have this little one hooked up in there. The 2 windings wound together as one continuous winding with a center tap. Just as normal, right in there. And then there's the negative side of the battery connector, and there's a 1 ohm current viewing resistor on the negative rail of the apparatus, which goes to the emitter of the transistor there. Okay, so this is a standard Joule Thief circuit with the positive of the battery connected through the switch, connected to the midpoint of where the coils, that mid connector of the coils, where the 2 windings of the coils are connected together. Okay, so this is not a laser saber variant. This is the standard Joule Thief arrangement. Alright, and then here I have some batteries, and then I have scope probes. The A channel is across the battery, so we're looking at the battery input voltage. And then the B channel is across the 1 ohm current viewing resistor, so we look at the current drawn by the entire system. Okay, so first of all, let's see if we can get it to light up. This is a AAA battery, and put it in there. And I think that one is really, really low. Let's see what it says on the Simpson, if I can do this with one hand. Just a moment, please. Okay, the Simpson is telling us that battery has only about 400 millivolts left in it. So it's really, really dead. And that's with no load. So let's see if it'll light that. Yeah, it does. It lights the LED fairly well. And when it's running, let's see what that battery voltage is when it's actually running. Okay, so here we have a Joule Thief starting on a voltage of about 400 millivolts and running on a voltage of 383 millivolts. And it's even doing that with all this extra resistance in the circuit too. So let's see what we see on the oscilloscope. A channel baseline there, B channel baseline there, and we're set at half a volt per division on the battery with no attenuation of the probe, and 0.05 or 50 millivolts per division with a 10x attenuated probe on the current viewing resistor. And let's turn the channels on, and there you see that 400 millivolts of the battery voltage, or 380 millivolts. It's still glowing, but there's not enough current to actually trigger the oscilloscope and show on the current trace, even with this extreme sensitivity of my oscilloscope. Alright, but we've shown that this Joule Thief does light an LED on some ridiculously low voltage. So let's go ahead and put a bit better battery in there. Let's try this one. Woo, man! All right. Yeah, that's too bright. Let's try this one. All right. So there's another AAA battery. Let's see what its voltage is. This seems some. Alright, under the running condition, that one's about 600 millivolts. Alright, I got a lot of dead batteries. And that one is giving us a current trace. There's your 600 millivolts on the voltage trace. Right? 5, 6. And then the current trace is still not quite strong enough for it to actually cause a stable trigger to the oscilloscope, but we are seeing a little bit of current there. Alright. So that's good. So let's go to an even stronger battery then. I think that would be this one. Yeah. That one's really cooking. Alright. So let's see what the voltage is on that battery. I should have just hooked this voltmeter up with clip leads, I guess. Come on. Alright, that's more like a battery that's not yet depleted, 1.367 volts on that one. Okay, so it's still underneath, well below what a fully charged AAA will do. But you can see that that blue LED is definitely glowing very brilliantly. And now we do have some usable traces on the screen here, so let's see what we got. Alright, so let's go back to the zero baselines, right? Zero baselines for the A channel and the B channel. The A channel is showing the battery voltage of half a volt, 1 volt, 1.4 volts, just about, right? And you can see that there's a little ripple on there. And the B channel is showing the current across, or rather the voltage drop across the current viewing resistor. And that's what that looks like, okay? So remember where the zero baseline is. So we have current, and then the battery voltage drops a little. You see that little ripple on the battery voltage right there? So the current goes up, the battery voltage drops, current comes back down. So it's triggering along in there. And that channel is at 50 millivolts per division, and that's across a 1 ohm resistor, so that translates to 50 milliamps per division then. So here we have 100 milliamps in that short spike, and then going down to about nothing. So if you take that and average it, that might be just a few tens of milliamps, 20 or 30 milliamps, because that spike duration is not really very long. There's a lot of dead time in there. Okay, but what about this ripple on the battery? What are we going to do about that? How do we read that? If I simply raise the magnification of the channel, if we start down here at 5 volts per division, we see that we still have 1.4 volts, but it's barely part of one division. 2 volts per division, alright, we have 1.4 volts. 1 volt per division, starting at the baseline, 1.4. Half a volt per division, starting at the baseline, half a volt, 1 volt, 1.4 volts. But we still haven't resolved that ripple. If I go to the magnification that's necessary to show that ripple, it disappears off the screen. up here, right? And I can move it back down, but then I lose my baseline reference, right? So how the heck am I going to visualize that ripple? In fact, it may move so far up the screen that I can't bring it back down with the channel position indicator. Oh, sorry, it's this one. So what do? Well, if I just want to look at the ripple, and I already know what the battery voltage is, then I can use the AC coupling function. All right? Remember how before, when I changed the amplification, that trace went up and up and up, right? Well, when I select AC coupling, now the DC voltage is blocked, the trace will stay on that baseline, and only the average of, or rather the average of the rippling oscillations will be on that baseline, not the DC offset voltage, which will be way up here someplace, right? So now I can change the channel amplification until I see that DC voltage in there, or rather until I see that oscillation on top of the ripple, or on top of the DC voltage. You can see that the baseline is here, so it looks as though I've got some negative voltage happening here. If I forget and don't realize that I'm on AC coupling, I might be tempted to conclude that there's a negative voltage going on there, but of course there isn't. Okay? And the magnitude of this ripple from peak to peak is about 2 full divisions, and we're at 20 millivolts per division there, right? Or I'm sorry, yeah, 20 millivolts per division. This probe, the battery probe, is not attenuated, so this is 20 millivolts per division. So we have about 40 millivolts peak to peak of ripple sitting on top of that 1.4 volt battery oscillation, or battery DC voltage. And the way that we've been able to visualize that is by using the AC coupling feature of the oscilloscope on that channel. Okay? Thank you for watching. Sorry we went so long.